It's really all about computing. It's all about speed. How much of this really vast universe, how many of the 400 billion stars in our Milky Way galaxy can we explore looking for someone else's technology? And today, the tools I use are 14 orders of magnitude, 14 factors of 10, better than Frank Drake was able to use in 1960. And that improvement is going to continue and continue at a faster and faster pace because our computing capabilities are improving exponentially. And for anyone who's ever studied an exponent, things double and then they double again, and that doesn't seem very much. But after you get through a number of doublings, in fact, you're making changes at an enormous rate. So everything kind of happens at the end. We've recently built a brand new telescope to do SETI and radio astronomy all of the time and simultaneously. And with that telescope, in the next 10 years, we expect to be able to observe at least 1 million stars, maybe 10 million stars, over a wider range of frequencies, simply because the compute power is there and it's getting better every day. Well, what we're looking for with our radio telescope is a signal that doesn't look like the kinds of signals that nature produces. So when natural sources of emission like pulsars or molecular clouds or hydrogen gas emit radio signals, they spread it across the spectrum. They sometimes it's relatively limited, sometimes it's completely broadband. But we have the ability with our technology to create a radio signal that's a single tone, a single channel on the radio dial, if you wish. And it's very detectable against the background noise if you have the right detectors. So that's what we've been looking for. Something that's obviously engineered, something that nature, at least as far as we know, can't produce. Now, that may be the wrong thing. We might have guessed wrong. We might, as we get more computational capability, we might be able to look for other kinds of signals that occupy more of the spectrum but still appear different than the signals that natural sources emit. So if you can imagine a two-dimensional screen and it's full of snow and static, like an old analog television set, right, which wasn't getting good reception. But on that two-dimensional display, imagine a line that's drawn, and it can be straight up and down, or it can be slanted. And if that screen is displaying two dimensions, one of frequency and one of time, that line would be a signal at a single frequency. And if it was straight up and down, that frequency would be constant. If the line has a slant to it, the frequency is changing in time, and that might well happen because the transmitter is accelerating with respect to the Earth. We're also now beginning to look in the optical part of the spectrum, not just the radio. And whereas in the radio we look for frequency compression, we look for narrow signals, in the optical what we're looking for is time compression. We're looking for really bright flashes that last a nanosecond or less. Now, as far as we know, again, that's the kind of thing that nature can't do. But with the right detectors, even when you're looking directly at a star, you can see a bunch of photons showing up in a single nanosecond against the background. And if you found such a thing, it would certainly suggest a technology, an engineered signal. Well, on Earth, we currently leak a lot of signals, broadcast television, for example, radio. The signals are intended for our local neighborhoods, but in fact, many of those signals go on beyond the Earth and travel and spread out in a bubble around the Earth that gets bigger 1 light year per year. So we're announcing our presence inadvertently. That's going to change in the future as we change our means of broadcast technology and go to direct TV kinds of deliveries and digital. But actually, even the satellites that are delivering the signals have some leakage out the backside of them, so we'll never go completely radio quiet. But we're not actually deliberately transmitting signals to different planets. We now know about 455 planets around other stars, so we're now beginning to know about some of the places we might decide to transmit to. But we're not doing that. And the reason is we're actually too young, right? We're a very young technology in a very old galaxy. So with respect to interstellar communication, we've had appropriate technology for maybe 100 years. The galaxy's 10 billion years old. So we don't know whether there are any other technologies out there, but we do know that we're the youngest that could participate in interstellar communication. Anyone younger than we are, with less technical capabilities than we have, can't yet be part of a conversation. And the odds are, in a 10 billion year old galaxy, that anyone else's technology is a lot older than ours. So right now, it seems to me that it's appropriate to let the older technology do the heavy lifting. So transmitting is harder than receiving, so we'll put that job on them. And then, if we ourselves get to be an old technology, if we grow up, if we in fact cannot get ourselves organized to be able to take on projects that last not 2 years or 5 years, but 10,000 years or 100,000 years, which is what really you need to do if you're thinking about transmitting purposefully, then when we're older, it would be appropriate for us to begin to transmit. And of course, by then, I hope that we could answer the question about who should speak for Earth and what should they say.